All right, let's get us started. So today's lecture is about deep learning. Uh, the field has changed so much that the intent of this lecture is not to teach you deep learning. I'm pretty sure many of you guys who are in research already know enough. So the purpose of this research is to basically put everything in perspective and give a little bit of preparation for the following lectures. So to give you a bit of motivation, there has been a lot of investment in deep learning since Google have acquired DeepMind, and there has been lots of startup, some with only 3% who has been acquired by Google. And nowadays, you see startup popping up right and left, and there are a lot of excitement in deep learning, and even you see that these terms popping up in New York Times, for example. So the appeal of deep learning is that uh, so far has won many of the pattern recognition competition, and it needs minimal amount of feature engineering, which is quite appealing in many of the applications. The field has gone over lots of ups and downs since 60s, and we have seen the waves of going the field becoming popular and less popular since 60s. So what is new right now is that now we have uh, more more powerful hardware such as GPU and right software that can make accessing such a powerful tools accessible to many of the people who are not experts, for example, in GPU programming. There has been a lot of research on coming up with better nonlinearities and better optimization techniques that make some of the development in deep learning more stable over the past few years. So overall, deep learning follows the general recipe of the machine learning, that we have some training data. So let's say that X is your input image, can be anything, and Y is whatever that you want to predict. And you want to choose a function that accept X as an argument, produce Y. And Y can be a single label or it can be anything more complicated than that. And at the end of the day, we have some sort of like a loss function that measures the discrepancy between what you predict and what the ground truth is. So examples of that, for example, the input can be image and output can be as simple as a tag for that image. And examples of the functions can be as simple as linear regression or a multi-layer neural network. And the examples of the loss function are things such as cross entropy and mean square error. So at the end of the day, we want to fine-tune the parameters of this network, if you wish, or the model that we have, minimizing the loss function. We usually form an optimization problem and use stochastic gradient descent. And here we go. That's basically the general recipe of what we do in machine learning at the end of the day. So to compute the gradient, there has been a lot of progress, and I would say this is probably one of the biggest progress in deep learning field and in general machine learning, that nowadays is not as painful as it was before, maybe even like I would say 6 years ago, that computing this loss function gradient does not need manual computation. So you can write your function in for example in NumPy even, and take a gradient of that, and so it's less error prone and it's really easy to compute. It's really easy to profile, and it's very easy to prototype. Also, on the other end, there has been a lot of creative thinking on how to come up with this function to predict the target, whatever that target would be. So today we're going to talk a little bit about that. Yes.
What happens when your objective function has something like maximizing, or which wouldn't definitely be differentiable? Like
You can do subgradient. You can still do subgradient. In the context of deep learning, most of the time we are dealing with a function that are differentiable, and so you can do many other things. If you are really interested in having something that is non-differentiable, either you can do something like a homotopy method that smooth it out and then change the smoothing level to make it almost as close as non-differentiable and do the gradient. So the outline of the talk today is that we're going to give a little bit of background on deep learning. Again, if you have taken course, for example, with Roslan, you already know all of this. So I'm just going to give, I want to have the same language so that next time, in the next class, and then we are talking about intersection of deep learning and graphical model, we use the same terminology. So let's just start with a very vanilla version of the deep learning. So probably this is the most simplest possible deep learning, network is a one-layer regression. So it's going to be very shallow, but that's the common structure of all of these approaches are starting from there. So you want to predict y, and x is your input here. I have to say that here by circles and arrow, I'm not talking about conditional independence. I'm just saying that x, all of those pass through some sort of like a contribution or parameter, which is theta, and then going to predict y. So this here, by arrows, I'm not talking about the graphical model. So the linear regression is the simplest possible neural network with only one layer. So here, for example, our input images are a bunch of images. Our input data are a bunch of images, and we want to predict the labels, which is like face versus not face. Very simple logistic regression. So our input image, so of course I cannot show the high dimensional input image, so let's say that I have only 2 pixels. So this 2 pixel image, you want to find a mapping from this 2-dimensional space to the target label. So that's what this function fitting boils down to. And so in the context of classification, we have pixel as an input image. We have parameters that combine all of them in a linear way and passes through a function, which is a logistic function that computes the probability of the target. So this, as I said, this is a building block to build a vanilla version of the graphical, the neural network. So the difference between this shallow network that I mentioned earlier is that instead of going directly from x to y, they put some intermediate variable in between, that those intermediate variable are, for example, in this case, is a linear function or nonlinear function of the input images. And then the final output is a linear function of those intermediate layer, which is hidden layer. And you can easily extend this to multiple outputs. So it doesn't have to be one output. So you can have the output can be like multiple tags for input image, or can be pixel values. The tag of the pixel value if, for example, you want to predict the segmentation. So building something which is deeper than that is as easy as basically viewing this as sort of like a modular. You can basically view this in a modular way. To build more network, you introduce intermediate variables. That is, intermediate variables is a, let's say, linear or nonlinear function of the previous layer, and you build it on and so on and so forth. This is basically the general idea of the vanilla version of the deeper networks. So what is the reason that we do this is that the premise of deep learning is that as you go from lower layers, which are inputting pixel image, to the output layer, which are the tag of that image, as you go from the low level to the higher level, the layers in between try to abstract image into more meaningful information. For example, you started with a pixel, the next layer is going to be edges in the image, edges in a different direction. As you go further up, you're going to get a piece of for example, if you want to do face recognition, it's going to get the pieces of the image, for example, eyebrow, eyes, nose, and so on and so forth. And then as you go higher and higher on the hierarchy, so the network start putting these pieces together. And if you somehow visualize, and I'm not going to go into detail, visualize the representation of the higher level, the very high level is going to look like the understanding of the neuron on the higher level is going to be faces. So, and this is the general idea that as you go from lower level to the higher level, you construct different levels of abstraction of your input, whatever your input is. So in this case, an image is very easy to visualize. If you have something more complicated, you can still apply the same idea. So, so today we are going to use the MNIST data as a sort of like a running recipe to introduce some kind of old ideas. So starting the beginning of the wave, probably like around 2006, and see how the idea developed over the time, and we are where we are right now. That deep learning has been many of the benchmark for many tasks. So let's start with the first idea. So the first idea that I told you at the beginning was that, well, the simplest deep learning deep learning method, neural network, is the network has only one layer. So let's say that we are given a bunch of images of the digits, and we want to classify them into 1 through 9. So let's build a simple linear classifier that predicts the label of the MNIST digits given the input. So the recurring theme to compute the gradients, because as I told you, at the end of the day, you build a network, and then you have to learn the parameters of that. The main ingredient of all of these approaches is to be able to compute the chain rule. So let's say, for example, if I have very simple network that X is my input image, and I have introduced some intermediate layer U and pass it through some sort of like a function, linear or nonlinear function, to predict Y. So in order to take a gradient of the Y with respect to X, I should be able to compute this simple chain rule. So it's basically as simple as gradient of the Y with respect to intermediate layer, an intermediate layer with respect to previous layer, and so on and so forth. And this has been the engine of basically all of the deep learning method that we have seen even today. So for the simple example that I gave you, so let's say we start with very simple linear regression. Our input image is X, so let's introduce some intermediate variable A, which is inner product between our parameters and X, and we pass that through a nonlinearity, and at the end we have sort of a loss function which is between our prediction Q, which is probability of the class being 1, and the ground truth. And this is basically how we build our forward model. To compute the gradient, we have to compute the backward, if you wish, message. And this backward message is basically, we should be able to compute the gradient of the J, which is our loss function, with respect to Q, and then Q with respect to A, and then A with respect to thetas. And this is all chain rule. And if we introduce extra variable in between, so you can view this as sort of composition of the function every layer. So in the first layer, I have my input image. I compute some sort of inner product between xi and some parameters. I pass it through some nonlinearity. I introduce another one, pass it through nonlinearity, and so on and so forth. And you can add these modules, which is like function composition. Function 1 composed of function 2 and function 3, and so on and so forth. And this is the recipe to build a multi-layer network. So if I have neural network of more than one layer, the recipe is the same. We have input image, some parameters, some linear, some inner product passed through nonlinearity. Again, you compute, you basically repeat kind of this module again and again. And a backward computation is basically computing the chain rule. And this is how we do this. The progress these days is that if you were a graduate student maybe, I don't know, 10 years ago, you have to do everything by hand. Now, we have so many tools that can do it for us. There's not error prone, you don't have to double check it again. And you just have to play with the parameter of the gradients, stochastic gradients. So let's start with some ideas and see how it behaves on these toy examples that I told you. So what would happen if I train very shallow network to predict the label of the MNIST data? I'm presuming that everybody here knows what MNIST data is. So it's an image of the digits. It's like you can think of it as a matrix of 28 by 28. It's a handwritten digit, and they have label for that. So this would be, if you use very simple linear regression, the error would be close to 2%, a little bit less than 2%. So back in 2006, there was not that much of access to deep learning, and if you want, GPUs, and if you wanted to train even such a simple network on a CPU, you should have waited a really long time, because think of if you want to build the deep neural network has a lot of layers, regardless of the implementation time and making sure that everything works, you have to let it run for a really, really long time. So people said that, okay, so let's play with a different idea. So what would happen if I pre-train each of the layers of the network? So I'm going to explain what the pre-training is. So it's basically the pre-training, the general idea is very simple. So if you have a layer of, let's say, 10 intermediate layer, you can construct, you can learn the parameter of the intermediate layer pretending that that's a shallow network. That's much easier to train because, first of all, if you only fix one with respect to one layer, and if the loss function is convex, it converge very quickly. For example, if your loss function is a regression, it even has a closed form. So it's very easy to pre-train the network and concatenate it on the top of each other. They did this, and then the result was actually worse than shallow network. So what goes wrong? Yes?
I have a question. Does that like layer by layer training looks like coordinate descent? Or
No. They did. So basically, let's say that I have 5 layers, right? So if I have 5 layers, you can think of it as like one shallow network, another shallow network, another shallow network. So the idea was actually much simpler than that. So input image is just a bunch of pixels. You provide your input image, and then you cut the rest of the network and assume that those are what you have. So you train your linear regression with respect to that, and you fix the parameter. And then when you want to train the next network, you view the intermediate network as an input, pretend that's a linear regression, fix the parameter. So you can think of it as a coordinate descent, except that in each coordinate descent, you go all the way till you cannot move anymore, and then fix it. In the next layer, you go all the way till you cannot fix anymore, so on and so forth, and then you don't go back. So you can think of it as one iteration of the coordinate descent. Got it? Yeah.
So in your previous slide, that performance was without retraining.
This is. Oh, sorry. Okay, so I jump ahead of myself. So this was the result of without retraining. So basically, they said that what would happen if I have a deep neural network, and with whatever we had back in 2006, which was not basically no GPU, pretty much. And what would happen if I just train it end to end? And that was the result. And so they said that, well, I expect this one to perform better than this, because this includes the other one, right? You can think of this multi-layer neural network as a now we are talking about capacity and all of that, but this has much higher capacity than this shallow network. How come it doesn't perform that well? Huh? It turned out that it wasn't really overfitting. So it turned out that they didn't wait long enough. Didn't converge. And the reason that we wait long enough is that the iteration doesn't take that long. Back then they didn't have GPU. They just run it for CPU. Okay, one day it reached plateau. I don't know, this is not convex optimization. It reached plateau, it should be converging. So let's stop. So what goes wrong is that maybe we got stuck in local minimum. So the problem is by no means a convex optimization problem. Maybe we have a bad start. Maybe the reason that we reach a plateau was that we had a vanishing gradient. So I'm going to talk about each of these a little bit. So why do I say that is a non-convex problem? The non-convexity is basically everywhere in deep neural network. Even the simplest quadratic function objective is not convex, not to mention the complicated cost function that we have in deep neural network. So this is the result of very simple quadratic function of two variables, x multiplied by y producing z, and the result is not convex. So the hypothesis back then was that maybe we start from a point because it was random initialization. So the stochastic gradient descent went up and got stuck at the local minimum. And if you go and look at the entire landscape of the objective, this is far from the global objective. But we have no way to measure it. That like, is it a good local optimum? Is it the local optimum or global optimum? So then they said that, okay, what would happen? So what would happen if we train each of these layers separately? So the idea was that the idea I just told you earlier, that we know how to, we have a lot of very efficient optimizer for linear regression. What if we pretend that the other layer does not exist, cut the other layers, and learn a bunch of linear regression? So, and fix the weight, and then keep constructing on the toper layers. So the other problem that they faced was that maybe the reason that didn't converge was that we didn't wait long enough. Maybe the gradient was not strong enough to take us from the plateau. So if you think of it, actually the vanishing gradient is a very serious problem. So all of these gradients that we saw so far had form of a function that looks like this: gradient of the previous layer and that previous layer with respect to theta. And if you think of it this way, it's kind of like if I call this A and call this one B, it looks like inner product of A and B. If at the beginning of the optimization I have A's and B initialized randomly, and let's say that for simplicity, A and B's are random with a Gaussian with mean 0. These should be what exactly? If I have A, a vector of Gaussian with mean 0, B is a vector of Gaussian with mean 0, this inner product should be correlation between A and B. And if they are independent, it's 0. So they thought that, and actually it's not an incorrect perception, that this kind of behavior happens quite a bit at the beginning of the training, because you have no idea how to initialize. And at the beginning, random initialization of the network was very popular. Hence, you see effects like this, that two networks at the beginning are quite independent. The weight of the previous layer has not contributed enough to this layer. So you can think of it as an inner product of two random variables. If they are mean 0, they're going to kill each other. So the idea was that, okay, let's pre-train the network. So we use labeled data. We start working bottom up. And in each layer, we're just going to train single linear regression, and then put the weights together and concatenate it without updating. And at the end, if we realize that, okay, so we put everything, maybe that's a better initialization, then we use that as an initialization and go through a few passes of the update of the entire network. So one idea was that maybe we started from the bad initialization, and the pre-training can be viewed as a good initialization. So let's do that. So they did this, and then, so basically the general idea, as I told you, was that they built the pre-trained network and concatenated them all together, and then the result actually improved. It improved with respect to doing completely random initialization, but still there was some sort of like a minor gap between pre-training and even shallow network. So it was kind of disappointing result. So another idea was that, well, this is still very expensive. It's true that we have to do pre-training, but maybe if we would have used some sort of abstraction of the input image, something that does not necessarily depend on the labels, but it depends on the structure of the data, and that might be a better initialization. So what if we pre-train the network totally unsupervised? So that gives us a leverage that you can use even much larger data set. And if we have this kind of abstraction of the data, maybe that's a better starting point. So what is the general idea for that? Instead of using supervised pre-training, they use unsupervised pre-training. So instead of using labeled data, they use unlabeled data. Again, they build the network bottom up. So build the first network, and then fix the parameter of the first network as an input for the next layers, and build the second layers and second layer. And then they concatenate everything together and did a few steps of the fine tuning of the fully supervised. Yes.
What is unsupervised training?
I'll tell you in the next slide. So the idea was that this was our original neural network, right? They cut the layer on the top, and they said that, okay, we need to have something on to predict. What if they can predict the inputs? So it's kind of like an autoencoder. So, and then I can use these as sort of like abstraction of the input image, get rid of the layer on top, and then continue. So very similar to the idea of the encoder-decoder. And then I can continue this construction, right? So the last function that I have is that how well my input image is constructed from my reconstructed output. And I'm presuming that if this is a good reconstruction, these are some sort of like abstraction of the input image. And I can continue building that further, right? I can use this as an input and basically use that as an input, build another autoencoder, keep this layer, and go on, and so on and so forth. Very simple idea. Yes?
If you train the model using autoencoders, so why don't you just link the input directly to the output?
So you can do that. So nowadays, for us, it's very easy to think that, like, why do you do this? You just don't even need the pre-training. But remember, back then, each of these steps took really long time, and they couldn't afford running this on a CPU. So they were thinking that, what if we start from something smarter, like our starting point is smarter? Yes.
So were you asking why for the pre-training you can't connect at each layer the input?
So I think you are trying to link output to input, right? So if you just compare input and with input, so how do you train to match the output?
I'm not sure if I understood the question and the answer, but I think one thing that it might seem like you were asking why, when you were training like hidden layer, you had to go through the first hidden layer. Is that your question?
No. So I think when you train model, you use the input as the output to test whether that hidden layer can extract enough information from the input, right?
Yes.
I think the goal is to match the input to the output.
Output. So
why?
So I'm gonna build that. So if you wait like one more slide, I'm gonna show it to you. So what they did was that, okay, so am I going forward? So what they did was that, so let's just start with the very first layer. They said that maybe that's not a good starting point. Let's have a starting point that it encodes the input image. Forget about output for a second. I want to have a way of encoding information in smaller bits that produce a good reconstruction, and I'm going to forget the output for a second, assuming that is a good abstraction of the input image. Hopefully that result in good output. So they build this autoencoder, and then so you can view this as an input right now, and build another autoencoder on the top of this, right? Right. This is the autoencoder for this input, and you can continue doing this. And then here comes your question that, okay, at the end of the day, you build some sort of like an autoencoder that abstract the input into smaller code. But that's not what I wanted. I want to predict y. So they said that, okay, that's true. I'm going to get rid of the last layer and put the y at the top. And then do a little bit of fine-tuning of the layers from there. Did I answer the question? So they use this as initialization. Assume that this is very quick initialization. I only have to solve autoencoder of one layer, right? And I can construct it incrementally. And I pretend that's a good input. And at the end, I'm just going to do a little bit of fine-tuning at the end. So the network that you build maps input to output, but with a better initialization. So it was three ideas. The first idea is that train the model end-to-end. The second idea is that do pre-training in a supervised way. The third one was pre-training with an unsupervised way. So the result actually resulted into a sort of like a significant gap between a shallow network and unsupervised pre-training. So back in the state of the art back in 2006 was that, okay, so the network with more parameters beat the shallow network. So that's a relief. You have a network that has a higher capacity. We expect that to perform better. But it's important to have a good initialization. The thing is that now in 2010, we don't do any pre-training. The reason that we don't do pre-training is that we have access to much better hardware these days that we can afford to wait longer. So the state of the art 2010, which is 8 years ago, is not to do any pre-training anymore. And it turned out that the reason that we got stuck back then was that, well, we should have waited long enough. Back then we couldn't afford, now we can. So no need to do pre-training anymore. Yes?
But wasn't another problem not just that you wouldn't convert, but you would get stuck in a suboptimal, like, local optimum. But,
right, yeah.
And when you do pre-training, you're effectively like regularizing, you're getting rid of some of these options by starting in a regime where you are closer to certain optimums than others. So you basically eliminate some options. So there's a chance that even though you can run it fast, you might still do better if you tried the unsupervised pre-training, right?
Yeah. So let me answer that from 2 points of view. So first, global optimal versus local optimal. We still don't know the landscape. We don't have enough tools to characterize the optimization landscape of the neural network. So in that sense, I would say we haven't progressed that much, but we have made some progress. So the progress is that one of the main questions that is asked nowadays is that, do we even care about reaching global optimal? So, and there are some theory that says that if the landscape looks like a bunch of bumps and these bumps are all in the same height, why do you even care to reach the global optimum? You only care about reaching global optimum if the global optimum is much higher than the local optimum. So if you can show that all of these global optima are equally good, if you reach to one of them, you're fine. So that's to answer the first question. The second question is that, does pre-training put you in a regime that avoids the plateau? I'm not sure we have answer to that. So I'm not sure that actually pre-training put you in a regime in a provable way that we can assure that it's put us in a better regime. I'm not aware of any publication that says that, yeah, pre-training does better.
Yeah, I haven't seen one either, and they're all hand wavy things because they can't say it for sure.
Yeah.
It just seems to be like in practice, sometimes people try it and it doesn't matter.
Yeah. So the third thing is that so regardless of all of that, so it seems that we don't have the theory. Does it work to do pre-training? One answer that I have to that is that yes and no. Yes, if you can do it, because in the neural network we could have come up with a scheme that pre-training makes sense because we can view each of these networks as a different initialization and then feed the neural network. Nowadays we are feeding much bigger model, and it's not very clear how we can do pre-training. So if we can do, and it's like extra coding, and if the idea is to fast prototype, it kind of defeats the purpose. But from practical point of view, if you have a model that you think that has the capacity, and you do the optimization with the hardware that we have today, it doesn't do well, try pre-training. But you have to come up with a way that how to do pre-training in a creative way. Okay. Yes. Yeah. All right. So this is basically state of the art. Not today, 8 years ago. So the goal was we want to find abstracted features. Training can be tricky because of the non-convexity and vanishing gradients. And unsupervised layer-wise pre-training can help, although it depends on your structure. So let me move on. So this is kind of like a historical perspective from 12 years ago, more or less. About back then when the new wave of the deep learning was not started yet. So we keep talking about, so this is the graphical model class. So how does it have anything to do with the graphical model? So it seems that this is a function, we are coming up with more creative way of building this function. How does it relate it to what we have been discussing in this semester? So it turned out that the first deep learning paper back in 2006, when the wave was started, was training a particular flavor of the deep learning called belief network, which happened to be a graphical model. So let's review that a little bit. So the main purpose, so let's say that I'm given the MNIST data set, and yet let's think for simplicity that it's a white background and black foreground, zeros and ones. And I want to fit a density function, px, that can generate digits like this. So my problem is a density estimator problem. So hopefully by now, you're convinced that the entire class of the graphical model is about density estimation, except that we impose different structures to it. So the idea of the sigmoid belief network, so here I have to say that here the arrows in this network represent a graphical model. So here is different than what I showed you earlier. Circles and arrows represent random values, and arrows represent conditional dependence. So let's say that so my digits, like 28 square pixels on the last digits, are put in the visible layer or observed layer, and I have set of hidden layers that are influencing the next layer to produce finally my last layer. So this is unobserved layer, and this is observed layer. So if I have, let's say, 8 in 28 by 28, this is concatenation of all of these pixels in the last layer. So what is the structure of this graphical model? The structure of this graphical model is actually very simple. We are assuming that so conditional dependence is just a sigmoid function. It's a very simple graphical model. Is the structure clear? Yes.
So why do you need a function like a step function?
So okay. So here I'm representing. So this is condition. It's a Bayesian network. So each of my CPDs has to be normalized. So I'm saying that this is the parent layer, pass through some sort of a weight, and at the end should produce something that I'm assuming that all of these random variables are binary, 0 and 1. So the conditional should produce something that represents the probability of that node being on and off. Does that make sense? Okay. So you can think of this, the joint distribution of the entire network as a bunch of sigmoids all multiplied with each other. And at the end produce this digit. That's it. And it's very simple network. It's normalized because each of the conditional dependence is just a sigmoid function multiplied to each other, and I want to generate a digit that looks like a MNIST digit. That's my goal. So what is unknown here is that I don't know how to put these weights. So I have this conditional dependence, but I don't know how to learn these weights. So I have a directed graphical model with unknown weights, and I want to learn it. So let me have a little bit of digression and introduce constructive divergence, and we get back to this concept quite a lot in the rest of the class. So if I want to, so let's say that at the end of the day, we want to minimize some sort of like a loss function. This loss function can be minus log of the likelihood, or any loss function that you care about. So we have a data and set up parameters. In the case of graphical model, this loss function is minus log of probability of the data given some parameters, right? So if I want to so that's the general maximum likelihood fitting criteria in graphical model. So for a general graphical model, most of the time we do have access to the unnormalized version of the density. We may not know how to compute the log partition function, but we usually can evaluate the nominator, which is the unnormalized version, using the potential and so on. So if I decompose the loss function, it becomes basically two terms, which is the log of the nominator, which is the unnormalized version of the density, minus the log of the partition function. And you have seen this in the context of undirected graphical model. Hopefully this is familiar to you. So if I want to learn the parameters, the first term usually viewed as plugging in the data that is coming from so-called empirical distribution and making expectation with respect to that. So that you can view this as just as a function, and we are drawing sample from empirical distribution that nature has given us, and just plugging that in a computing average. So I'm just writing the same function in a different form to view it as sort of like expectation. I haven't done anything so far. But the problem happens when you want to compute the second term. And if you want to take a gradient with respect to W, you have to compute the gradient of the first term and the second term. First term is easy because most of the time we can evaluate this term, and given all of the fancy tools that we have these days, we can compute the gradient as well. But how can we compute the gradient of the second term? You guys have already seen this quite a lot in the context of undirected graphical model, but I want to give you a little bit of different perspective. And this is, I would say, common approach, and it still is in some extent, called contrastive divergence, that is used for the cases that the log partition function cannot be computed in a closed form. So what is the general idea? The general idea is that at the end of the day, if we want to find the best parameters, we want to compute the gradients. So I want to compute the gradient of the W's. I have to be able to compute the log of the partition function. So the log partition function is just that part is just computation of the gradient of the log, and that boils down to computing the gradient with respect to this integral. So this is the definition of the z. You guys have seen this before, so I'm not going to fill that in until somebody else fills that in. So you already have seen it, so help me to fill in between. How can I go from here to here? You have seen it at least 4 times. Any idea is welcome.
Yeah, so the derivative is with respect to W, so we can
Yes.
take a derivative inside.
Okay, so I'll put the derivative inside. Okay, say it again. Okay, so that's the general idea. So multiply and divide by what? Huh? Yes. Oh. Okay. What is this? If I bring that inside, what do I get?
This is the problem.
I'm going to normalize probability, right? Okay, and then is an expectation of the term inside, whatever that is. And that turned out to be log, right? Is a log of, okay. Yeah. So you have seen this in a undirected graphical model. So if I put everything together, I have the first term, which is expectation with respect to empirical distribution versus expectation. And then you see that the form of these two are identical, right? So as if you want to say that at the optimum, that the gradient vanish goes to 0, these two should be equal. The gradient of the score, this is the score, called score function. Score function with respect to empirical and with respect to best variables that you see, if you compute expectation with respect to empirical and with respect to actual computation of the expectation, should match with each other. So you're basically the force that drives your parameters is a contrast between them. So these can easily be computed from the sample, and the other one needs sampling. So now the hurdle that we have to pass is that this is easy to compute. What should I do with this? Because although this is easy to compute, I can compute the gradient of the log of the unnormalized function. I still have to compute sampling. I have to do sampling. So one idea is to basically do MCMC for sampling. You remember that for the MCMC, all you need is to have access to this unnormalized distribution. And you just cook it, let the boilers work, and then come back and it's cooked. The problem here is that you have to wait too long till this actually converges. So the intuition of the Hinton et al. Was that at the beginning, you only need to move forward toward the right direction. The direction doesn't have to be exact direction because you're going to go over so many hills and ups and downs. If it's roughly right, who cares? So instead of running the MCMC all the way to the end, we can run it for, let's say, 50 iterations or even 1 iteration. Well, 1 is too little, but few iterations. You don't need to wait that long. And it's going to give you approximate estimation of this gradient, and then you go along. And it works practically well. Another way of saying this is that, remember the computation of the log of the p was, so I'm just basically following the same thing, writing the computation of the log, integrating out all of the latent variables that I want to get rid of, and then bringing the gradient inside, and then writing the expectation with respect to the joint distribution. Now, what I have here is a term that looks like a posterior. So another way of writing this is computing expectation of the data. So X encodes both observed and unobserved. Here by X, I mean this is X. So you can think of the expectation of the observed data as if you're sampling from the posterior distribution and plugging that into joint distribution and summing over all of these latent variables. And similarly for the log partition function, I don't go through the detail, is you sum over all of the observed and unobserved random variables. So at the end, your gradient, I'm just saying the same thing that I told you earlier, just saying it in a slightly different way, is that the first term is averaging over the posterior, the second term is averaging over the observed and unobserved data. So the way that they view it is that you can think of this model as sort of like a sleep and wake up. In a wake up mode, the model is exploiting the parameters that it is right now. And when it goes to sleep, it tries to explore the space and it dreams about the landscape of the optimism. It's sort of like a weird analogy, but it's an analogy that is stick to the field. So this is something called wake-sleep type of algorithm that in the wake, it uses the parameters and basically it computes the first term and basically use whatever belief that it has with respect to posterior because it boils down to computing the samples from posterior. In the sleep mode, it tries to sample from both H and V's. So now let's go back to our sigmoid example. So for our sigmoid example, the Z constant is 1. Why is it 1? It's a Bayesian, right? All of the terms are normalized. There's no second term. So the gradient of the second term goes away. And you can work it out. It's not actually very simple to do that. But if you think about it as, so you only have the first term. That is basically, if you remember, it was minus log of the P. So in this case, there is no P star because everything is normalized. Oops. And X are drawing from the data, right? So it's only first term. For the simple logistic regression that we have, if you actually work out this term, it looks like the input image, probability of the input image multiplied by the input features. The first term becomes very simple. So this is also called the delta rule. So it's like as if you're predicting something, you compare it with what it should be in each of the pixels and go along that direction. So if X and Pi match with each other, the gradient vanish. So it is in some sense, looks like sort of like a expectation maximization. You estimate what the visible point should be. So for example, let's say that you have a bunch of pixels, and you estimate how the probability of that pixel would be, and then you compare that with xi with the actual values, and you go around that direction. So it has a flavor of expectation maximization. You compute the expectation is unobserved, you compare it with the real value, and that's your gradient.
So why can't we do like a hard count EM, in which we can just compute the maximum, the image that has the maximum probability and compute the gradient with respect to it?
You can do hard EM. Well, I guess in the hard EM, computing some of these expectations in closed form would be difficult. So your Z is 1. But remember in EM, you substitute all of the unknown random variables with the current expectation. I'm not sure that would be a closed form. So instead of doing that, you say that, I don't know what that would be. I'm going to do sampling and average them all together. That's my estimate. It's kind of like a lazy way. So again, going back to our sigmoid belief network. So in practice, CD or convergence divergence doesn't work, at least for sigmoid network. So sampling from the posterior, so the problem here is that one of the steps of the CD was computing this sampling, and this sampling does not converge to the actual values quickly. So the take-home message from the sigmoid network was that it's easy to sample from it, but it's easy to, like when the model is learned, it's easy to sample from it because everything is normalized, but it's hard to learn the parameters. So then one may say that Okay, so if it is so hard for directed graphical model, what about undirected graphical model? So to do that, let me review a little bit of the Boltzman machine that I think I introduced in the first few weeks of the class. So you can view the Boltzman machine as an undirected graphical model that the potential between two random variables is written as an expectation of a matrix that falls between two vectors of xi. So let's say that xi's are vector. So the potential is expectation of the bilinear function between xi, wi's, and xj. So if I say that in English, these basically enforce xi and xj to be similar. So for simplicity, let's assume that this is scalar, scalar, and a scalar. If this is positive, you have high potential whenever these guys have the same sign. That's what it boils down to. Make sense? So now let's say that I have a graphical model. All of the xi's and j's are binary or scalar, just binary random variables. And I have a bunch of weights that I have to learn. So these are the parameters that I have to learn. And all they do is that, assuming that this is positive, they are enforcing xi and xj to be similar. If you put negative values here, you are enforcing them to repel each other.
One can even think of this as a normal distribution with zero mean and W representing the variables.
So the problem here is that it doesn't have the normalizer, right?
Yeah, but I mean the distribution would still tend to a Gaussian.
So xi's and what if xi and xj's are binary? If it is Gaussian distribution, it doesn't produce binary, right? It's free. So that assumption does not apply here. So again, I can rewrite the entire thing as a factor network. It's very simple factor network. So let's go back to our original example that we were trying to do. We are trying to build this MNIST data set. It's the most important data set in the world for whatever reason. And our input image is our digits. We want to generate digits, but here instead of directed graphical model, we have undirected graphical model. This is our visible pixels. This is our visible pixels. And this is our hidden random variables. The difference here is that we are going to encode the relationship between unobserved and observed random variables with a bunch of unnormalized factors. Right? That's all. And this is more or less the vanilla version of the Boltzman machine. This network has some sort of interesting properties. So first of all, you don't see any connection between these hidden random variables, right? So conditioning on observed, which is here is V, HI and HJs are independent. That means that I can do Gibbs sampling very easily. I can observe H, sample HI and HJ, and they have nothing to do with each other. And also, the posterior of HI condition on posterior of the H given the posterior H condition on V is kind of the belief network. I'm going to go over that a little bit more. So, what would happen, as I told you, is that HIs and HJs are independent of each other condition on V, observed random variable. What would happen if I do Gibbs sampling? So here, what do I do in the Gibbs sampling? I start from the initial distribution, condition on V, and generate H. Right? That's what we need in the Gibbs sampling, right? We somehow if I want to sample from the variable in the middle, I condition on the Markov blanket, compute the normalized distribution of the variable in between, and sample from it, and continue. So kind of I can view this as a Bayesian network. So if this is H and these are V's, I have to compute H condition on V, and this has to be normalized because I want to draw a sample from it. So you can view every step of the Gibbs distribution as if you're drawing sample from a single layer Bayesian network, a sigmoid network. Make sense? So if I'm at iteration t equal to 0, I'm conditioning on V, sampling from H. Next iteration, condition on H, sampling V. Condition on V in the next iteration, go on and go forth. Go and so forth. Right? Yes.
Why did you say a sigmoid function? The function you showed was a quadratic function for potentials.
Yeah. So let's say that my hidden random variables are also binary. Remember what I was saying here? And I'm assuming everything here is binary, right? So here, what I'm doing here is that this binary, the join, everything's binary. I'm conditioning on V, sampling from V. So it's kind of a sigmoid function going forward. Condition on V, I'm generating H. And it should be normalized, right? That's the whole idea of the Gibbs.
Yeah, I don't understand why the normalization of that function ends up to be sigmoid.
So what was the sigmoid Bayesian network? One single layer Bayesian network. Single layer sigmoid Bayesian network was that some sort of like a layer on the top, H1 through Hn, and they're going to produce V's. This is the simplest case. This is V's, and this is H's. Right? This is exactly what you're doing here. When you're generating this, you're conditioning on H generating V's. Is every step of the Gibbs distribution does this operation for single layer. Make sense? Because the structure that you're drawing sample from is exactly the same structure of the sigmoid network. Now, if you run this Gibbs network, you can think of it as concatenation of the infinitely many sigmoid Bayesian network. So what we do here is that we condition on observe random variable, draw sample from H, condition on H, draw sample from V, and so on and so forth. So I can view this as if I'm drawing sample from infinitely many layers of sigmoid network. And now the question is that how can I learn the parameter of this network? Remember the idea that we introduced at the beginning about, well, at the beginning, a few slides back about CD, contrastive divergence. All I need to do is computing the clamp phase or wake up phase, or another way of saying that is Hebbian learning, and free phase or sleep phase. And that's my divergence. Remember we introduced that in conjugate grade, in CD, when we were talking about CD. And at the end, effectively, we are drawing sample from RBM is equivalent of drawing Gibbs sample from RBM is equivalent of drawing sample from infinitely many layer sigmoid network. Make sense? Now the thing is that it was easy to draw sample from sigmoid network. It's hard to learn the parameters. What we did was that we flipped the problem on the top of its head and saying that what if I don't have one layer? I just have like infinitely many layers. And I let the Gibbs sampling run. And in infinity, assuming that I run the Gibbs sampling for infinity, so the drawing sample from that is as if I'm drawing sample from infinitely many layers of the sigmoid network. In reality, I'm not going to draw infinitely many samples. I'm going to draw finite number of samples. But the number of layers would be very large. So for example, I may run this Gibbs sampling for 1,000 iterations. Because remember, when I was talking about the CD, I said that in reality, nobody runs the MCMC till convergence. They just run infinite for finite number of layers because they care about approximation. But what we did effectively was that by going from directed graphical model to undirected graphical model, we make the learning of the parameter easy. And that was the trick. One was easy to draw sample from, sigmoid network. The other one needs Gibbs sampling, hard to draw sample from. The sigmoid network was hard, difficult to learn. The Bayesian network, because of the CD, it's reasonable to learn from. And there is a one-to-one mapping in a sense that drawing sample from RBM is as if you're learning a sigmoid network that has many, many, many layers. You never build it explicitly, but this is what the steps of the Gibbs does for you. Does that make sense? So that's a trick that we did to avoid the weirdness of the learning of parameters in sigmoid. Yes.
So when you say many, many layers, you mean each layer corresponds to one of the samples of the hidden state?
Yes. So every steps of the Gibbs, you just go from one phase to another phase, another phase, another phase, but as if you are drawing sample from every layer of the sigmoid. So that's the same. So mathematically, it becomes the same. But you probably have seen something similar to that when we were learning CRF. So remember, when we were learning CRF, we introduced, so remember we wanted to do part of speech tagging, and we said that sometimes by removing by making everything dependent, which makes our learning difficult, we avoid sort of like a weird behavior of the parameters. If you remember that. So when we were training the CRF for part of a speech tagging, we introduced three models. One was HMM. The other one was sort of like a normalized CRF. The other was unnormalized CRF. And unnormalized CRF worked better because all of the path was dependent, and it makes the learning better, and we don't get stuck in we didn't have the label bias. So in that sense, it's kind of similar flavor. So again, to say the same thing. So this is the RBM, and we want to generate sample from it. Because it's unnormalized, we have to run the Gibbs sampling for many, many iterations. But in every iteration, one can view drawing sample from Bayesian network, sigmoid Bayesian network, except with one constraint, that parameters of each layers are all the same. That's basically equivalent. So, and effectively by doing this trick, we managed to make this problem more manageable from learning sigmoid network, which are hard to learn but easy to sample from, to switching to another network that is infinitely deep. Is difficult to draw a sample from, but it's easy to learn. So now let's go back to our MNIST example. Yes.
Even though the network is infinitely deep, the number of parameters are still limited. Right?
Yes, because they're all tied together. Yes.
So how does that help the expressivity of the model by just having multiple layers even with fixed number of parameters?
So that depends on how. So depends how the width of your network. So you can still increase the number of parameters by having a lot of intermediate layers in between. So you have some sort of a trade-off. You can have a lot of neurons in between, but you're tying all of these W's together. So in that sense, you can still increase the capacity of the network. Another question is that, so I'm going to show you an example that what would happen if I use this in the same MNIST example. So if it's a good learning, it should produce good distribution. If you draw a sample from it, you should produce something that looks like MNIST. It should be good for prediction. So let's apply it on MNIST. So what is the setting? So instead of having autoencoder that is constructed progressively in the same scheme that we did at the beginning, we are going to have a full generative network that learns the parameter of this density estimator. And this, for us, this density estimator is going to be this RBM network. So what I'm going to do is that I'm going to pre-train the layers of the RBM in a greedy fashion. So to go back to your example, to your question, what I can do is that I can learn RBM for first layer, let it converge, fix that parameters, and pretend that what I have on the top is my training data. Train another RBM on the top of that, and this is how I can increase the parameters. So in that sense, kind of pre-training, but it's a pre-training of a fully generated model. Make sense? So I pre-train a stack of RBM, and then I'm going to unroll it. I'm going to fine-tune the parameters with backpropagation, just to make it comparable to what I did before. So what do I mean by that? So to pre-train the RBM, you have your input image, you have your RBM, you're gonna run your CD to learn WIs, and that become your data, right? You can sample from posterior, and that become the data for the next layer. You can train another RBM and fix the parameters, and so on and so forth. Does this part make sense? I'm going to do this. It's like as if you are doing RBM 1, 2, 3, 4 times.
So this is stochastic for each training example.
What is it?
So it's like you compute WI for each training example.
Yeah. So this one is easy, right? This one is easy. So your input, easy is that assuming that your RBM is easy to learn, you just run one RBM.
Yeah, but it's not just using one image, right?
So you use one, no, it's not going to use one image. So you're using all of your images, right? So remember, is a density estimator, right? The object that you are trying to learn the density of this high dimensional, 80 by 80 pixels, right? This is the density, you want to estimate the density of this guy, okay? But you're using all of your data. You can sample from posterior, generate new data, and then run another RBM. Learn posterior, generate data, another RBM, right? Now, I'm going to unroll it. So one W goes up, W transpose goes down. So I'm going to use this as an intermediate layer, so it's the W's, and their transpose is going up. This is just simple unrolling. Does this part make sense? How I'm unrolling it?
So you initialize these with the W's you had before, so W2 transpose it, like they're tied again, right?
Yeah. So they're tied again, but like if you think about RBM, going from V to H was W. Going from H to V is W transpose. So if you think of it as an autoencoder, one layer, the weight of one layer is W, the weight of the other layer is W transpose. This is what I mean by unrolling. So yes, so this W is the same W as here, except it's transposed. That's all. So then I'm going to use this. So this is going to be my autoencoder. Simple autoencoder that I train in a greedy way. And so I assume that it's a good initialization, and all I do is that I just train an autoencoder end-to-end using the parameter of this guy. It's just fine-tuning the parameters. Then I'm going to get rid of the last layer and fine-tune the entire data with the classifier. So pre-train the RBM, fine-tune the autoencoder, and fine-tune the parameters. So let's draw some sample from the data. This is how the first one is how the real data look like. And this is the 30-layer deep autoencoder. And as you see, the results are pretty good. And if you compare the results with, for example, the same number of dimensionality, if you do PCA or logistic PCA, you see that it's much sharper. So it seems that the density of the data is learned pretty well.
So that's the reconstruction?
Yes. Yeah. And it's basically reconstruction.
So you pass in the raw original image, not a noisy version.
Yeah. And so this is basically you pass in the raw image, you see how well you could reconstruct, but you can also draw sample from it because it's fully generative model. It was not something that you can do from simple autoencoder, right? From simple autoencoder, you can view it as only denoising. You bring input image, they reconstruct something for you, but you cannot generate new data. Now, because it's fully generative model, you can go forward. Like you can start from the top layer, generate, and then generate the last layer. And this is if you draw a sample from the trained model. I would say relatively, I mean, for that time, 2007, it's pretty realistic. I mean, now we can build it much stronger model, but you have to put yourself in a 2000, almost 11 years ago, and the results are relatively realistic. So what would happen if I use that for classification? If I use this scheme of classification, the results actually improves with respect to state of the art for digit classification, and it's like roughly the error is around 1.25%. Yes.
So I'm a bit confused about how we went from stacking RVMs to classification. You showed the unrolling, and then you just lop off the top layer and then put the classification after.
I believe this result is with no example
as pre-trained weights for something.
I think this is the result of probably fine-tuning of because you can do the same thing, right? You can remember the unsupervised pre-training. You can use this for unsupervised. Put the last layer and just fine-tune the parameters or only use the last layer for pre-training. But nothing changes that much. Yes.
When you say last layer, are you mean the unrolled layer that has the same dimensionality? Or
No. I think the code, the layer in between. Because you use one RBM, another RBM, another RBM, and then you go to 30, cut the rest, put the Y there. So in that sense, you can think of this as a sort of a generative network that we use as a teacher for the supervised network. Again, that is back in 2007, and it's so much that we can improve with MNIST. It's just only 1% left. You can work more than that. So when you go to 1% till the possible maximum improvement, you've got to switch the data to something else. All right, so what about deep Boltzmann machine? So what I showed you at the beginning was that one layer Boltzmann machine was equivalent of learning infinitely many layer sigmoid network. What if you have infinitely layer of the Boltzmann machine? Or like not infinite layers, like in many layers. One layer was equivalent of infinite layer sigmoid network. Multiple layers would be even more powerful. So we can use basically the same idea. So there is nothing that can stop us from learning the multiple layers of the deep Boltzmann machine, except the computational cost. So the general technique is basically the same. We have undirected graphical model that the potential function between the binary random variable xi and xj is some sort of exponential of this bilinear function. And again, the same wij's that enforce them, xi and xj, to look similar to each other if they are positive. Now we have a set of observed random variables that are all, again, binaries, v's, and a set of unobserved random binaries that are h, that are our hidden units. So if I have multi-layers of the sigmoid function, at the end of the day, for an arbitrary connection between observed and unobserved, I can write my likelihood function as the log of the unnormalized version as a quadratic function. So this E is, remember, our P and X is P star V and H divided by some Z of theta. And here what I'm showing here is that I'm defining E, V, H, and theta as minus log of the P star. This is the energy of the network, right? And here the theta means all of the parameters that I don't know. All of the interaction between observed random variables, the interaction between unobserved random variables, and the interaction between observed and unobserved random variables. Is it clear how the energy function looks like this? Remember, our potential look like this. Xi, W, Xj, right? If I take a log, it's going to be Xi, Wij, Xj. This is the log of the phi. I can complete this for all of the random variables in the network at the same time, and at the end, what I have is look like this. It's just it is an easier way of writing it, right? So my theta right now is L, W, and J. Make sense? So now what I want to do is that my PV, and so this is a normalized again. What I told you at the beginning is that the normalized function is integrating observed and unobserved random variables of the exponential. If you want to compute this in a closed form, this is really expensive because all of these are binaries, and you have to sum over 2 to the power of some of these random variables. It's gigantic. So we have to resort to the approximation technique. At the end of the day, the CD technique is basically here to help us. So we have to so gradient with respect to W, L, and J boils down to computing expectation with respect to empirical data and an actual expectation. And this is how it always boils down to. So if you want to compute expectation of the W, which is the term between all of the observed. So remember, the W was the term between observed and unobserved. So the gradient of the W become expectation of the VH, observed, unobserved, with respect to empirical data and with respect to model data, and so on and so forth for the rest of it. Computing these terms is easy because you just substitute. But to compute the other one, you have to do MCMC. And although the full conditional, because everything is binary, is easy to compute, for a large network is very hard. And even for MCMC, it may not converge. So one idea would be, what would happen if I know how the forms of the posterior would be? Everything is binary. Why not using variational inference? So the idea of the variational inference is that I can have an approximation of the posterior that looks like, because if H is binary, this is going to look like some sort of like a sigmoid function. And so is this. So I can keep an update of my sigmoid function, draw a sample from it, compute this gradient, and update my belief. And this basically performs much better than MCMC because you don't have to wait until everything converges. You just keep the form of the belief that you have with respect to your unknown random variables. You update the parameters with mean field, the general mean field idea, and progress. So, okay. So this is basically the way that we can learn a general deep Boltzman machine. At the end of the day, the deep Boltzman machine boils down to the energy of that, which is the log of the unnormalized version, is some sort of a quadratic function, and that's how we learn the parameters. So what would happen if we use that for pre-training and use the parameter of that for learning the data? So in the interest of time, I'm not going to show you that, but let me just show you the representation, the latent state representation of the digits for the PCA versus the result of the DPM. And as you see is that Each of these colors are one of the digits. So for example, 1, 2, 3, 4, 5. And in the latent space, if I use, for example, one of these embedding methods, such as TSNE, to embed each of these digits in the lower dimensional representations, things are much more separable using RPM than PCA. So it's very natural to expect that if you apply classification on this space, things are much better separable. Is this plot make sense? Each of these dots here are one of the digits, and each color represents one of the numbers. So this is basically, that's it. So lots of things to explore, lots of different nonlinearity and different structures of for learning features. My goal was to give you a general perspective of how things was 10 years ago, or maybe till 2011. So in the next class, we are going to combine deep learning and graphical model and talk about things which are more research these days. Thank you.